Okay. It is. Oh, okay. Take down a couple notes on this, okay? I'm not going to say how many, but yeah, back your phone was good. Computer.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 47. It's on heat exchange. It's hard to say, don't touch this iron right here in the middle. It's hot. What does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object. And we call that transfer heat. And so what we're really doing is transferring energy as thermal energy, or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there, because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading across. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button, and now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call.
So he just showed how the energy that was inside the block, the iron block, was transferred out to the water. What term or what concept is describing how that energy is just flowing from one to the other, but it's not being lost? What concept is that? Energy is not lost. Law of conservation of energy, just like the law of conservation of matter applies, law of conservation of energy applies, and you did see that on your web quest and on your lab from yesterday. But which of these would have a negative Q associated with it? The iron metal piece, that block that went in, because you got to always think about, if I'm losing, I should have a negative Q, and the water in this case was the surroundings, and it's gaining, so it should have a positive Q. And that was one thing that a lot of us had a little mishap on our lab from yesterday. Your Q that you calculated for the water in the lab yesterday, was the water the one losing or gaining energy? Well, hold on. What were the two pieces of our pie here? We had water and ice. Okay, so was the water the one losing or gaining energy? It was losing. That should have had a negative Q associated with it, because the ice was gaining energy, which was the positive Q. So when we went from like number 3 on the analysis to number 5, number 3 should have had a negative Q, because that was in the perspective of the water. But number 5 was talking about the ice, so you switched modes, and that's where he referred to the positive blah, blah, blah heat diffusion. So that's why, keep that in the back of your mind. You should be thinking about system surroundings a lot of the times, especially when energy is transferred.
Equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. Remember, the Maxwell-Boltzmann distribution shows us how that works. If we were to look at it, this would be the cold body and this would be the warm body. Now, in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of the iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance. And so we use a term called specific heat capacity to measure that. And so right here, you can imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy per gram, and then Kelvin or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed. The amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold.
So what happens to the gold? What'd you say happened? It got hot. Not only just got hot, but it got hot very, very fast. So who's up? Okay, bye, Eli. It's Taylor. So the gold got hot very quickly. Why did it get so much hotter, so much faster than the water? So you're right to say it has a lower heat capacity. I can see the 0.126 versus the 4 here. But who feels good about explaining why? James? Not quite. Because every unit is important when you talk about specific heat capacity. Okay? So I want you to implement every unit there in your discussion, your explanation. Give me what you got. How about it absorbs less energy to increase 1 gram by 1 degree Kelvin in this case, but 1 degree Celsius is most of what we say. So it's going to only require like a tenth of a joule to increase 1 gram of that substance by 1 degree Celsius. So once it absorbs, let's say 1 joule, well, 1 joule is, there's like about 10, not quite. But if I call that 0.1 joules, if I absorb 1 joule, and its specific heat capacity is 0.1 joules, it's gonna increase by 10 degrees Celsius. Whereas this 1 joule, how much is that really going to increase the water's temperature? Barely any, 0.25 degrees Celsius, because it needs 4 joules of energy to increase it by every 1 gram by 1 degree Celsius or Kelvin. So it requires a lot more energy to actually cause some temperature change, whereas this one requires, you just look at it and it's going to start heating up, okay? Because it requires very little energy to actually start heating up. And that's why you can see at the same amount of time, the temperature changes are vastly different.
The aluminum are heating up more readily than the water. Now, the energy is going to be the same. It's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to kinetic energy transfer due to molecular motions? If you did, you learned what I wanted you to, and I hope that was helpful.
A little bit of an idea here. Okie dokie. Number 10 is really easy. So go ahead and look at your, will you hit the lights for me? Look at your true false for a second while I finish checking a couple of the homework. Everybody get your phones away right now. Ask you to count. Cannot be pressed right now. There's ones that ask for that methanol and ammonia and such. You can look at this about your textbook. I did page 522. I was like, Okay, can I go past the true false? Which one? What's your question, Alina?
I was just wondering about
Number 9. The equation, blah, 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 blah. Examples of the thermochemical equation.
yeah, sorry.
Oh, okay. You don't have to say I'm sorry. It's good. Okay, let's start with number 10 from the problem's perspective. And do I have it right here? Yes. Okay. How much energy is required to convert 3.6 grams of water, so that's for mass. Okay, she's good. From negative 5 degrees solid to vapor at 175. So who can tell me just in 30 seconds or less the process of setting this up? Alina.
I usually draw like a feature just say, but then you have like Q1 and Q2. Well, Q1 is like the graph going up, so that's the MCAT.
Okay, because there's temperature change.
Yeah. The Q2 would be like the fusion.
So phase change. Okay.
That would be like H, delta H.
Mhm.
MCAT, delta H.
So in this case, we're going to have how many Qs? 5 Qs because we have 5 instances of variation between temperatures. So whenever you guys see anything going from a very low temperature to a very high temperature, think about where the phase changes occur. Well, we know water, boom, 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 kind of, okay? So this is -5 down here, and then this up here at the very top is where I'm recording 175. What if I had said it only heated to 35 degrees Celsius? How many little stairs would we have? If I said it heated to 35 degrees Celsius. So how many Qs would I have? I'd only have 3 because I'd have to heat it from its cold temperature as a solid up to its melting point, which we know water melts at 0, and then it would phase change, and then we would have about halfway up here would be our 35 mark, so we'd only have 1, 2, 3 to deal with, and so that might be one thing you might think about when we get to our quest, which is not here yet. So, our quiz, our free response. So I may not ask you to go all the way, so you got to think about the temperatures where they are, where the inflections will occur. So once you get here, you're going to realize that you do have 1 Q down here, which is going to be MCAT, and that mass is the 3.6 grams. What's the C for solid ice? 2.05. So the C is 2.05 joules per gram degree C. So you'll take your M, which is your 3.6, times your new specific heat capacity, which is just a slightly different for the different phases of water here. And then the delta T for this one is what? Say again? 5, because you're going from 0 to a -5. So 0 minus a -5. Always do your T final minus your T initial. So your delta T here is 5. And I'm just doing basic setup right here, okay? And then our heat of phase change, so this is Q1. Heat of phase change for this right here is our Q2. Scott, tell me how to set up Q2. Say again? Okay, so he converted his 3.6 grams of water to, using the mole mass of water, 18 grams to moles, because this is the one that utilizes moles, and then
multiplied by 6.01
kilojoules per mole. So this one's in kilojoules, and this is our delta H of fusion. So when you're doing your Q2, you're using the delta H of fusion because it's melting. And I was talking to, I think it was Allie yesterday, the value for delta H fusion, I told you guys to write down in your foldable was this, right? 6.01.
Mm-hmm.
I told you from when I was walking through notes, I didn't look at my constants before. I think I told you 40 point what for? I told you 40.1. I was thinking of this one here. It's 40.6, 40.7. It's different in various constants that are published online versus textbooks and versus other things. And I'll give you the delta H of fusion and delta H of vaporization. So use the ones that I gave you for that specific one. I was trying to do the water one for my head. It's like 40.6 or 7, and that's the one that I commonly use in my work. So if your answers were just a little bit off, it might be because of something like that, like a decimal being off. So we'll work with that in just a second. So the next one would be Q3. What would Q3, how would that be calculated? Paige, how would Q3 be calculated here?
3.60.
So the mass times,
4.18.
and that 4.18 joules per gram degree C is the specific heat capacity for liquid water, and then what would the temperature change here be? And so we've already gone from the solid to the melting point of 0. We've gone through our phase change. Now we're going from our liquid all the way up to where it's going to start to boil, which is what? 100. So what's the temperature change here? 100, because it's 100 minus 0. So you do need to probably mark these little tack marks on the side of your axes. So that's going to be 100 there. Okay, so your setup is very similar to Q1, but Q3's got a different specific heat capacity. Q4 is our next phase change, which is delta H back. So similar to Q2, but the setup includes a different constant versus the delta H infusion. So Q4 is moles, which Scott gave us here, times our delta H diffusion, which is 40.6 kilojoules per mole. So that's a lot bigger than the delta H diffusion because of the difference in intermolecular forces that you're overcoming there. And I would also say that whenever you're talking about intermolecular forces, this is where potential energy is changing. So potential energy, because it's still energy being added, right, across the x-axis here. Heat is added or energy is added, however you want to state it. So as you go up the curve on the slope, what kind of energy is being added there? Say again? What kind of energy is being added on the sloping parts here? So I know heat and energy are being added the entire time. We have two forms of energy, kinetic energy and potential energy, which would be increasing on the sloping lines. Kinetic, because kinetic energy is directly related to temperature. Remember that definition? Temperature is the average kinetic energy of a sample. So if kinetic energy is increasing on the sloping parts here, here, and here, potential energy has to be the thing that's increasing on these flat parts. Because the kinetic energy is not increasing, because the temperature would be increasing. So we can't have kinetic energy increasing. Therefore, that makes us say something has to increase because it's getting more energetic, and that would be the potential energy in that case. Okay, so Q4 is similar to Q2, and then Q5 is similar to MCAT with the other values. So the mass is the same. The C value for steam is 2.02 joules per gram degree C. And the temperature change for that last part would be what? 75, because you're going from 100 to 75, or to 175. So 75 would be our difference there. So that one does take a lot out of you. Okay, I know that's a big one. But I'm trying to keep these to a minimum because I know that it just requires a lot of calculations and making sure you're remembering the two different types of problems, Q equals MCAT versus Q equals fusion or vaporization. On number 9, oh, I know what happened on number 9. Do you guys realize that it says a sample of metal on number 9, metal is boiled in water. So that tells us our initial temperature of the metal, which would be what? 100. So if you set up your low calorimetry table with Q or M and M, C and C, delta T, it's the initial temperature of the metal that would be 100, and they both always end up thermal equilibrium at the temperature final, which in this case is 55.2. Okay. In terms of other types of problems, there's only 3 types of problems related to thermo. Is there anything else that you're like, I have no idea what I'm doing? Yeah.
I added it up against the 12.4.
The 12.4. Yeah, that's closer. I have to look for my actual stuff. So, but is your process is good. You understand your process? Good. Stick with that for now. Yeah, Nicole.
So we're supposed to use the formula of Q equals mole delta H diffusion.
Number 7.
Yeah.
How many moles of acetone can be melted by the addition of delta H? How many moles of acetone can be melted by the addition of heat with sublime with viscosity? What was your question? Did you use the what?
Like, which equation do we have to use? Because I thought we had to use the Q equals mole delta H diffusion.
Versus MCAT? Yeah. Yeah, you would definitely, since it's talking about a phase change, that's fusion. So you would say how many moles. Basically, take your Q is equal to moles times delta H diffusion and divide by, so the Q is given here at blah, blah, blah kilojoules, and then divide by your delta H diffusion for acetone. But you'd have to look in your textbook for the acetone delta H diffusion, which I'll give you on your test, but there's no problem set. You'd have to look. And so what was that one? No, Allie, you looked at it, didn't you? What was the delta H diffusion for I used ammonia. Did y'all say ammonia or acetone number 7?
Mine says ammonia.
Yours is ammonia because I changed it, and this is an old problem set. So you had to look up your delta H in the book, but 5.65 should have been the one for ammonia. And I'll give those to you at the very top of your paper. Yeah. Yeah. I tried to make sure everything's there for you. Yeah. I will, there's two different values for, well, the one that we use most commonly is our liquid water, 4.18. I expect you to kind of know that one. And I'll put it on your paper, no problem. But the other ones are phases of matter differences, and there's a reference sheet. I just have a blue reference sheet over there. And they have all these values for specific heats, and I'll always give them to you. They're just on your paper, or if not, they're in your textbook. Okay? Okay. Let's pull out our phones real fast for Kahoot. I'll answer more questions after this. Yeah.
It's like, I got the right answer, but I used
Which one? Use what?
175.
You should use some. I teach this now 1 through 5 because the specific heats are different. But the some people sometimes just teach just 3 different ones because they just don't consider the different specific heats. So if that's maybe something you're thinking of, I'm not sure. Okay, so yeah, go for it. Ready to join? Okay, 4, 6, 3, 3, 3, 4. Yep. Yep. And you, of course, guys, use your foldables, use your open notes, do what you gotta do. This is a really easy 9-question Kahoot. And if I cut the lights down a little bit. Okay, let's do this thing. I'll write the Chem on the board. For those of you who need it still. I'll try to write it big. You can see my voice working it. 4, 6, 3, 3, 3, 4. Okay. This says a pirate steals jewels. Endo or exothermic? Still on. I got the game pin over here for you. So keep lying on the game pins here. I'll help you with it in a second. Okay, good. So if it goes from bottom to top, and there's more energy going into the system because the products have higher energy, it has to go in, which is endothermic. Good. Nice. Does temperature measure potential energy or kinetic energy? Alina, go through hit next. Kinetic energy, good. One more time. Next one. Stall, okay. Accelerators. Calculate the initial temperature of a cup of coffee that is cooled down to 20 degrees C. The overall T was negative 34. This one's not hard math. Okay, first of all, I said it cooled down, people. So it's starting off higher and it's cooling down. So it's got to be one of the higher temperatures. And I believe none of them were higher than this one. Pretty sure. So down by 34 means from 54 down to 20. Okay, Next, this one's a little bit more intense. Calculate the heat given off when 122.9 grams of copper cools from 178 to 74 degrees Celsius. The specific heat capacity of copper is 0.385 joules per gram degree C. Alright, last 10 people. I give you a lot of time. 2, 1. Okay. Good! Yay! I don't really need to go over it. What was the formula? MCAT. And it was released, so it was negative. Good. Solve. Ready? Calculate the heat necessary to raise 48 grams of water from 97 to 190. The specific heat capacity of water is 4.18 joules per gram degree C. About this. Moving on. What is the melting point of the substance in the phase diagram? All right, so you can read a phase diagram, mostly. Okay, so the melting point is the first inflection point, and then the boiling point is the next one. Which region of the diagram shows only the potential energy increasing? All right, so the kinetic energies are where the temperature is increasing because those are directly related. Potentials are the plateaus. I literally just talked about that to make sure you guys were good there. Awesome. One more solve. I think one more solve. Okay, it did say added, so I'm thinking endothermic, and then Q equals MCAT, the specific heat capacity of water, 4.18 joules per gram degree C. Okay, one more. Oh, dang, I do have one more. Okay, last one. Grand finale. number of kilocalories of heat produced from the reaction of 15 grams of calcium oxide with excess water. Get closer if you can't read it. Scooch up here. It won't get any bigger. So it says 15 grams of calcium oxide with excess water. You've not determined the heat produced from the reaction given. And it says calcium oxide plus water yields calcium hydroxide plus 15.6 kilocalories. And just think of that in terms of energy.
Miss Enlow, I need Jasmine and Raylan to come to the office, please.
Give me 1 second. Thank you.
Thank you.
So most of us are working through this. Like who's not standing? Alright, last couple people. Okay. Ooh, let's go over that one then. Let us go over that one. Put the lights on for me. Thanks. Alright, so on that one, you had a balanced complete equation. Ooh, got one of those off. Just take one of them. Okay, great. So you had a balanced complete equation with calcium oxide plus water yields calcium hydroxide. And then you hadn't seen it specifically like this before, but it said it had 15.6 kilocalories, I believe, being produced. That energy is being produced. Is that exothermic or endothermic? Exothermic is being produced. It's exiting the reaction as a product. It's going away. It's exiting. Okay, so it's exothermic. But the question gave you 15 grams of calcium oxide. What does calcium oxide weigh? So about 56 grams, right? So 15, and you need it, since this is related to the delta H, which is referring to 1 mole of this is the number of energy associated with 1 mole, so that's our ratio, but you have to put this to moles first. So 1 mole of calcium oxide is 56 grams, and this is what we did yesterday. And then this amount of energy, 15.6 kilocalories, is produced for every 1 mole of the calcium oxide. So then you did that divided by 56 times 15.6 is about 14. Sorry, it's about 4.18. So does that make sense from our yesterday discussion from thermochemical equations? A little stoichiometry thrown in there? Yeah. This was just calcium plus oxygen molar mass. It was adding up from there too. So that's one that I didn't know if we would remember, but we did okay. All right, who's the annihilator? Oh, I know, annihilator. Okay, cool, gotcha. Okay, so now, any remaining questions on PS 17 that I need to go over conceptual-wise, calculation-wise? You guys feeling it? Final results, got it. Anything else I need to go over? You're going to take a 4-question quiz. Let's see how we do. Do it. Please. If you were sitting right, like, arm to arm with somebody, move to a lab station. And yes, you can have a calculator. You need a calculator. No. Why? Yes, if you have a periodic table without a bunch of scratch marks on it, go ahead and get yours out. But if not, I'll bring you in a second. This should take you no more than like 15 minutes, okay? After that, after you take your quiz, you're going to be working with a partner on the molarity total worksheet. You don't write on this. You can work with a buddy, and that's fine, but don't write on this. And then if you finish, go ahead and do reading at 15, which some of us have already done because we're overachievers. We didn't realize that. Reading at 15 is somewhere. not sure, you can write on the back of this. It may not be big enough, so if you would like a piece of paper, I'll go ahead and get that out now as well. If you need paper, I'll come to you. You already know it. If you need paper, I'll come to you. I'll look. I can take one after. Are we going to have my hey? I'll get you a board. I'll get you Please show your work in its entirety. And if there are no gifts, I might as well not even grade it. Because you didn't tell me that story.